Welcome to the presentation about our research on the neural networks for financial stability of economic systems topic. Bankruptcy prediction is essential for businesses, particularly in today's rapidly evolving economic landscape. Ongoing research is critical to developing precise and dependable models that adapt effectively to these dynamic changes. Neural networks do well in bankruptcy prediction by detecting relationships between variables and patterns that may elude other models, mainly when dealing with large datasets. These networks have universal quality, enabling them to learn from diverse data types and apply them in various contexts. The capacity of neural networks to understand complex relationships, adapt to assorted data types, and adjust their predictions based on new data renders them an indispensable tool in forecasting the financial stability of economic systems. In conclusion, neural networks are essential for companies striving to predict bankruptcy and make well-informed business decisions. Bankruptcy prediction models analyze a company's financial data to predict the probability of its bankruptcy in the future. These models can be helpful for various purposes, such as early warning, credit risk assessment, investment management, restructuring and recovery planning, compliance, supply chain management, and mergers and acquisitions. The selection of tools for building models depends on the goal of forecasting. Depending on the input data and output results, choosing a programming language and configuring everything properly is necessary to obtain a highest efficiency. Several programming languages can be used to develop neural networks for bankruptcy prediction, such as Python, R, MATLAB, Java, or C++. In our research, we used Python because it has many libraries and frameworks specifically designed for the development of neural networks such as TensorFlow, Keras, and PyTorch. Building a neural network to predict bankruptcy in Python requires a deep understanding of machine learning and financial analysis. The general steps to create a neural network to detect the financial stability of economic system are as follows. The first step is data preparation. Then it goes with feature selection, splitting the data into training and test sets, building a neural network. Then we train neural network on training data, evaluate the model on the test data, then we optimize the model, and then we finally can use it for prediction. These two diagrams on the slide show the total number of companies by business type and financial statements in available open data on official websites. However, this data is not uniform, making it impossible to make calculations, so the analysis is supplemented with companies from only big level section, contributing to the universalization of calculations. Here you can see the distribution of companies by business type inside the previously selected data. A uniform distribution facilitates comprehensive training of the model, delivering good results across various business types. The table presents codes from the Ukrainian financial statement and balance forms that we selected for the subsequent calculations. This slide provides a list of calculated financial ratios based on codes from the previous slide. The highest observed correlation between the financial ratio and bankruptcy status was for the return on assets ratio, with a value of 20%. Employing parameters with correlation ratio up to 20% in recurrent neural networks training is justifiable, as they can contribute valuable insights to discern patterns and associations within the dataset. Adopting a low correlation ratio threshold enables recurrent neural networks to detect and capitalize on nuanced, less pronounced connections between input variables, potentially enhancing the model's overall predictive efficiency. After we prepared the data, we built several types of models. On the slide you can see the optimized versions of them. The first one is a feedforward neural network. It transmits input data through multiple layers. Each layer comprises a set of neurons that perform linear or nonlinear transformations on the input data. This type of neural network is well suited for bankruptcy prediction tasks, as it can learn complex, nonlinear relationships between inputs and outputs, specifically the probability of bankruptcy. This versatility is beneficial for modeling a range of factors that may impact bankruptcy risks, such as financial ratios, economic activity, and non-financial data. The second and third ones are type of recurrent neural networks. Such networks can process sequential data where each input signal depends on the preceding one. They are particularly suitable for bankruptcy prediction tasks because they can learn temporal relationships between inputs, which can be valuable when analyzing time series data. Furthermore, recurrent neural networks may also help predict the bankruptcy of companies with a history of financial difficulties or financial performance that changes over time. Long short-term memory networks are recurrent and were introduced to solve the problem of vanishing gradients in recurrent networks by adding memory cells that can remember information over a long period. This architecture allows the network to selectively remember or forget information over time, especially when processing long data sequences. A gated recurrent unit network is also recurrent, but with a simpler architecture. During model training, we used the confusion matrix that provides information about the model's errors, while accuracy provides a simple assessment of overall performance. Combining these tools, one can better understand how well a model performs and identify improvement areas. However, it is essential to note that precision may give false results in cases where the distribution of classes is unbalanced. In such cases, it is advisable to use other evaluation metrics such as accuracy, recall, or F-score. The built neural network models have relatively high performance evaluation indicators, which indicates that they predict bankruptcy with a high probability. This is essential for a bankruptcy prediction model, as false positive predictions can have significant consequences. The feedforward model has the highest accuracy, precision, and F-scores, indicating that it is the best model overall in its ability to make accurate predictions and balance between accuracy and precision. The recurrent models have a lower precision and F-scores than the feedforward model, but higher recall scores. This indicates that these models can better identify actual bankruptcies, but at the expense of a higher number of false positive predictions. The relatively high false negative rates for all three models indicate a direction of improvement. False negatives indicate that the models fail to identify companies that will go bankrupt, which can have significant consequences for investors and creditors. According to the obtained performance indicators, the feedforward neural network model is the most efficient. However, it may be helpful to investigate false negative predictions further to identify areas for improving this model. In conclusion, the constructed models have relatively high performance evaluations indicators, which denotes that they predict bankruptcy with a high probability. It demonstrates how well the neural networks predict the financial stability of economic systems and allows us to identify areas of improvement. Thank you for your attention.